Why do high-speed ADCs suffer from timing inaccuracies? Imagine trying to catch a fast-moving ball with a camera that slightly misses the perfect moment. That's similar to what happens with high-speed analog to digital converters when they try to sample rapidly changing signals. These converters are essential in many electronics and embedded systems, but they face a common challenge: timing inaccuracies. High-speed analog to digital converters work by taking snapshots of an analog signal at precise moments, determined by a clock signal. When the clock is perfect, the sampling is accurate. But at very high speeds, tiny imperfections in the clock can cause the sampling instant to shift slightly. This is called clock jitter. Even a tiny deviation, just a few picoseconds, can lead to errors because the input signal might be changing very quickly at that moment. Think about a signal with a high slew rate, which means it changes rapidly over time. If the sampling happens just a fraction of a second too early or too late, the voltage at that exact moment could be quite different from what it should be. This small timing error translates directly into an amplitude error, meaning the digital output no longer perfectly represents the original analog signal. This reduces the accuracy and resolution of the conversion, especially at high frequencies. Other factors contribute to timing inaccuracies too. Power supply noise can cause tiny fluctuations in the digital circuits that control the sampling clock, making the timing drift. Electromagnetic interference and crosstalk on the circuit board can distort the clock signals, leading to further errors. In systems with multiple ADC channels working together, like interleaved architectures, mismatched clock phases or delays between channels can cause residual timing errors. These mismatches can create distortions or unwanted signals in the digital output. The clock distribution network itself can be a source of trouble. As the clock signal travels through different paths, phase mismatches and delays can occur, especially in complex systems with many channels. Input signals that load the circuit or take longer to settle can also cause inaccuracies because the ADC might sample before the voltage stabilizes. All these timing errors impact the performance metrics of high-speed analog to digital converters, such as the signal-to-noise ratio and the effective number of bits. Engineers combat these issues by using high-quality, low-jitter clock sources like crystal oscillators, designing careful PCB layouts to reduce noise and crosstalk, and employing calibration techniques to correct for mismatches. In real-world applications like radar, high-speed data acquisition, or communication systems, these timing inaccuracies can cause the system to misinterpret signals, leading to errors or degraded performance. That's why understanding and minimizing timing errors is so important when designing high-speed analog to digital converters.